I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we no, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Much of the following explanation is adapted from Nobel Prize-winning physicist Richard Feynman's lecture on physics, his section called Electricity in the Atmosphere. For every meter you go up in the air, the voltage increases by around 100 volts, or we could say around 100 volts per yard. We can draw these voltage increases using what are called equipotential lines. Notice that the ground is negative and the sky is positive with respect to each other. According to Feynman, this extends upward to 50 kilometers, or 31 miles. Where the air is very conductive. This is the case in fair weather. In stormy weather, like a thunderstorm, things are quite different, and I won't talk about that here. But if this voltage exists between your head and the ground, why don't you get a shock? The reason is that your body is a good enough electrical conductor that standing on the ground, you're basically a part of the ground. The equipotential lines would look like this. There's still effectively 0 volts between the top of your head and ground. Similar effects happen with trees, buildings, and so on. What about the electric current? A downward electrical current exists and consists of positive ions, molecules or clumps of matter that have a positive charge. These ions are moving slowly toward the ground. The current density from these ions is very small, around 10 microamps or 10 picoamps, crossing each square meter or yard every second. So in any small area, there's not a lot of power. And that's the explanation about atmospheric electricity adapted from Feynman's lectures.
Blue skies and sunshine today. State workers scrambled for cover. Their tornado drill was part of Severe Weather Awareness Week in Georgia, and part of staying safe in any storm is having an adequate heads up, as CBS 46's Renee Starzik shows us.
That instrument there, those antennas there, are the ones that measure the vertical and horizontally polarized spherics, the crackles.
It's scientific jargon to most of us, but what weather experts here at the Severe Storms Research Center are doing could make us safer.
You can't see, but inside that area there is actually my raindrop distrometer that measures each individual raindrop and its size.
The Georgia Tech Research Institute facility measures all kinds of data, from basic wind speed and pressure and humidity to the lightning strikes inside clouds. This is an electric field mill. It measures the charge in the atmosphere. During an intense storm, the atmosphere is supercharged. That helps meteorologists tell us when to take cover.
You know, anything that can give you another minute or two of warning, especially for tornadic storms, is terribly important. The one on the right is a spherics experiment that measures the electric breakdown in the clouds. You hear it on your AM radio when you hear the crackles.
All the information is logged and analyzed. Cutting even a few minutes off the warning time when a severe storm hits could save lives. Researchers here admit they dream of the time they can pinpoint the weather right down to the second, days in advance.
What happens in this particular subdivision next week at 4 o'clock, you know, is my Alta tennis match going to be rained out? But I don't know that we'll ever get to that point.
In Marietta, Renee Starzik, CBS 46 News.
Around the world, at any given moment, 2,000 thunderstorms are churning through the sky, producing up to 100 flashes of lightning every second. Lightning might seem like something we've got all figured out, but in fact, the details of the physics behind those flashes is still a bit of a mystery. Los Alamos National Laboratory studies lightning because it produces signals similar to those from a nuclear explosion. That understanding is helping us develop better instruments for nuclear test ban treaty monitoring and, in the process, allowing us to answer a lot of questions about lightning itself. For example, what initiates lightning? Some say it's caused by cosmic rays scattering enough electrons through the atmosphere to get a current going. But recent research conducted by Los Alamos scientists and their collaborators strongly suggests that lightning actually arises from areas of extremely high, localized electric fields, not from the long paths that a cosmic ray-induced event would require. We're also learning that lightning can be a useful tool. Research shows that enhanced lightning rates can indicate severe weather. Maybe someday our understanding of lightning will allow us to use space-based lightning detection to predict tornadoes and other severe weather events with enough lead time to prevent casualties. Until then, Los Alamos will keep studying and better understanding those mysterious, energetic streaks in the sky.
Every minute matters when it comes to preparing for severe weather. And now there's a new tool that can help keep people safe by providing earlier warning of Mother Nature's most dangerous storms. Dangerous thunderstorm alerts issued by Earth Networks indicate the increased potential for dangerous weather, including deadly lightning strikes, damaging winds, heavy rain, hail, and tornadoes, and often provide more advanced notice than traditional warnings. Earth Network's dangerous thunderstorm alerts are made possible by the Earth Network's Total Lightning Network, the world's largest network of lightning sensors, and the first to comprehensively detect both cloud-to-ground and in-cloud lightning. In-cloud lightning flashes account for the vast majority of lightning in the atmosphere, and more often than not, the first lightning in a storm is an in-cloud pulse. Thus, warning systems based only on cloud-to-ground strikes often fail to provide the earliest possible notification of a developing storm. Moreover, high rates of total lightning, the combination of in-cloud and cloud-to-ground flashes, are often linked to an increased threat of lightning strikes, heavy rain, high winds, hail, and tornadoes. With unmatched in-cloud and cloud-to-ground lightning detection efficiency, the Earth Network's Total Lightning Network is uniquely positioned to improve severe storm warning lead times. Dangerous thunderstorm alerts are automatically triggered when the total lightning activity of a storm cell exceeds the threshold associated with an elevated threat of severe weather. Each alert is depicted by a polygon that encompasses the alert area and is accompanied by a detailed weather bulletin listing the counties covered by the alert and the estimated time of arrival for locations in the storm's path. Alerts are updated every 15 minutes until the lightning activity drops below the severe threshold. Time and again, the Earth Network's Total Lightning Network and dangerous thunderstorm alerts have demonstrated the ability to significantly increase warning times for severe weather, ranging from life-threatening lightning strikes to destructive winds to potentially deadly tornadoes. These severe weather events often occur within 30 minutes of the first in-cloud lightning flash. Dangerous thunderstorm alerts are instantly delivered through Earth Network's Streamer RT weather monitoring and alerting tool for operations and decision support, and to consumers through weatherbug.com and WeatherBug desktop and mobile applications. They can also be received as a data feed to be ingested into a client's visualization system. When lives are on the line, the lead time provided by dangerous thunderstorm alerts used in conjunction with the vital warnings issued by the National Weather Service can be the difference between harm and keeping people out of harm's way.
So what excites me about this project is that it's a little bit out of the box. It's an area of research that a lot of people have worked on for a long time, and people have produced a variety of different types of results based on observations, but there aren't well-established physical mechanisms to explain some of these observations. And so another aspect of this project that excites me is that it's so interdisciplinary, and that we've had to gather a group of scientists together that come from very different areas of atmospheric and space research to work together in a way that they probably wouldn't have dreamed of before. And so we have people who work on the behavior of clouds, lightning, but we also have space physicists working on the interaction between the solar wind and the magnetosphere and the ionosphere. And not only that, but we cross disciplinary boundaries in that we have to work with electromagnetism, we have to work with chemistry, we have to work with other aspects of science that are usually not combined together into one project. And so that's part of what makes it interesting to me.
So we're looking at the role of thunderstorms and electrified clouds in the global electric circuit. So a cloud doesn't have to actually be producing lightning to be electrified. And there's what we call a Wilson current that generally runs from the top of the cloud into the ionosphere and helps feed the global electric circuit. So in the typical thunderstorm setup, it's a source of charge. In the reverse setup, or the opposite polarity, it's generally a sink. So we're hoping to find some parameters of thunderstorms, like we're looking at the speed of the updraft and how much ice is in there, and we're hoping we can relate that to how strong or weak the current is.
So I'm from Penn State University and Communications and Space Science Laboratory. In that lab for the last 10 years we have been very actively engaged in development of theoretical understanding of transient luminous events in the Earth's atmosphere. So we work on a variety of subjects related to lightning and lightning behavior, lightning physics, and of course in the context of global electric circuit modeling. We want to quantify how much lightning contributes to the global electric circuit, for example in comparison with electrified thunderclouds and electrified clouds. There is a significant controversy in existing literature as to how much lightning contributes. So in some cases, some scientists actually claim 40% of the total current which is flowing in global electric circuit is contributed by lightning. So we want to actually understand and quantify actual amounts.
Hi, I'm Eric Palm. I'm the director of the DC user facility here at the Magnet Lab. This is our 45 Tesla hybrid magnet. It's the world's strongest DC field magnet by far. It's a hybrid. It has a superconducting magnet on the outside and a resistive magnet on the inside. The superconducting magnet on the outside makes 11.5 Tesla, and the resistive magnet on the inside makes about 33.5 Tesla. Together those add to equal 45 Tesla. Everything weighs about 35 tons. Running flat out, this magnet uses 31 megawatts of power, and it costs about $3,000 per hour to run.
So where's the magnet?
As you look, the big silver cylinder on the side is the superconducting outsert. A lot of what you see is not the actual magnet. Off to the right side of the outsert is the supply cryostat and the big green things that are making noise there are the liquefiers that provide liquid helium for the outsert. In the bottom, coming out of the cylinder in the center, is the water supply for the resistive magnet insert. It takes about 3,000 gallons per minute of water running through this magnet to keep it from burning up. The water comes in about 45 degrees Fahrenheit and it leaves about 120 degrees Fahrenheit. So this is a really good water heater also. This magnet is the Guinness Book of World Record holder for DC field magnets.
Where do the scientists work?
The scientists do all their experiments from the top platform up these stairs People come from all over the world to do lots of different types of science in this magnet. There's science on semiconductors and superconductors, and mainly materials research where we're pushing the limits of temperature, pressure, and magnetic field to try to understand why materials behave the way that they behave.
In today's world, we've come a long way in terms of the capability to detect tornadoes, in terms of understanding how they form, in terms of understanding their behavior once they touch down. But the one thing that we haven't made as much progress heretofore is actually increasing the different types of technology that are used to detect tornadoes. There are multiple ways to detect tornadoes now, but in the past, those means of detection have been indirect detection. They've been using radar echoes, using radar that can detect particular formations and the bounce back from the radar and the interpretation required of that bounce back to determine that there's actually a tornado that's either forming or on the ground. An advance in technology that permits the detection of tornadoes directly is truly a welcome development in the field of tornado detection and subsequently in effective tornado warnings.
Majestic and untamed, beautiful yet dangerous. As danger silently approaches through power outage, loss of cell signal, even if electrical interference scrambles your weather radio, you will be warned. The world's first direct detection, personal tornado, lightning, and severe weather alert. Every second counts. Find out more at tornadoalert.com.
Sure, it's bright and loud. And scary. But if you watch lightning from space, you can learn a lot about storms, like how soon the really bad winds are coming, or hail, or tornadoes. You see, people are building this new satellite. It'll be like a superhero with magic vision, watching out for us all the time from high above the Earth. It'll take hundreds of pictures of the cloud tops every second to find lightning flashes, even ones that don't hit the ground. And if a whole bunch of lightning starts all at once, well, then the weather people will know that bad stuff is just about to happen. And they'll be able to give us more time to get ready. and go to a safe place. Pretty cool, huh? Sure, it's bright and loud, but it doesn't have to be scary.